Question set number 14 here. Question number 1 says a student uses a bar magnet to pick up a paper clip. The magnet causes what? This is one where we have to read through all the options, right, and see which one fits the best. An electrical potential difference across the paper clip? No. A bar magnet does not induce a potential difference across the paper clip. That's not even close. A transfer of electrons from the bar magnet to the paper clip. We don't want to get mixed up between electricity and magnetism. When we touch something that's negative to a paper clip, then we would transfer electrons to the paper clip. But when we touch a bar magnet to the paper clip, that's not a bunch of electrons. That's not a negatively charged object. That's not going to happen here, okay? We don't want to get mixed up again between electricity and magnetism. C, an alignment of domains in the paper clip, which results in the paper clip becoming a temporary magnet. That sounds pretty good, actually. That sounds pretty good. Let's just read our other option first here, just to make sure that it's not better. An alignment of the domains in the paper clip, which results in the paper clip becoming a permanent magnet. It's close. What's the only difference between C and D? Yep.
Temporary.
Yeah, temporary versus permanent magnet. So what does it become, a temporary magnet or a permanent magnet? It becomes a temporary magnet. The answer is C. You got to be careful in a question like this, right? If they had to flip those around and made C, D, and D, C, so the permanent magnet was the third one, there would have been some people that got to the third one, read it, and thought, oh, that sounds good, and then chosen that, right? Without even reading the fourth option. You should read all of the options just to make sure that there's not a better option. Make sense? Doing it this way, we're not going to get tricked by that because of the order that they're in. But if it's the opposite order, we might get tricked by that if we're not careful. The answer is C. 2. You got 4 diagrams here. We want to know which of those diagrams best illustrates the magnetic field surrounding a bar magnet. There's 2 things that I've told you to remember when you're dealing with electric fields and magnetic field diagrams. One of the things, specifically with magnetic fields, is that magnetic fields always point which way? Away from the north and toward the south. That is outside of the magnet, right? Inside it points the other way around, but outside from north to south. The other thing that I told you to remember is that when field lines join up, we get a force of attraction when they join up, and when they don't join up, we get a force of repulsion. We don't really need to use that in this particular question, right? Just the fact that it points away from the north and toward the south means the answer has to be D. No, I mean C. That's what I meant. C. Good? Now, you are going to get a question on tomorrow's quiz where you have magnetic field diagrams. I'm telling you right now, it's going to be a little bit harder than this one. It's going to require you to know that the magnetic field goes away from the north toward the south, and it's going to require you to know that if the field lines join up, they attract. If they don't join up, they repel. Got it? It's not a trick question. It's not crazy hard. It just requires you to know both of those things versus one of those things, like in this question. All right, next question, number 3. I've got a few questions over this one here today. We want to find the net electric field at point P due to these 2 magnets. We'll make this one the blue magnet. We'll make this one the green magnet, the blue north pole and the green south pole. Now, some people, when they see this question, a number of people, I think, when they see this question, want to think of this as saying, well, north pole and a south pole is going to be a field line that goes from the north to the south, kind of like this, right? You can do that. You can do that. And if you do, you realize that, oh, the field at that point kind of goes up and to the right. The easier way to do this, though, like hands down, the easier way to do this is to treat them independently of one another. That field line that we just drew is correct, but it comes as a result of the 2 field lines that are produced by each of these magnets. There's the field line that goes away from the north, and then independent of that, there's the field line that goes toward the south. The net electric field at that point is due to the field to the right and the field up, which means the net field at that point is up and to the right. Does that make sense? We did electric field problems like that, right? If you had a positive charge right here, and you had a negative charge right here, and we were trying to find the field strength right here, we would say, well, there's a field away from the positive, we would say there's a field toward the negative, and the net electric field would be up and to the right. So do them independent of one another. I can't remember if it's on tomorrow's quiz or your unit assignment or your unit test, but you get a question almost exactly like this, again at some point. At some point when it counts for marks. I just don't remember where you see it, that's all. So be ready for that. The answer for that one is D. And the last question has a Venn diagram. Venn diagram that you've never seen. That's fine. That happens. As long as we know what a Venn diagram is, right? Shows things that are the same and things that are different about different things. We have three things here that we're comparing: a gravitational field, an electric field, and a magnetic field. Where two of them overlap, that property, where two of them overlap, the properties within the overlapping are in common with those two fields. Where three of them overlap, then whatever properties inside that overlaps with all three of the fields, and so on. We've got four different properties here, or four different statements, and we want to know where in the Venn diagram these different statements fit. Can be directed toward the source. Let's look at all three of these fields. Can a gravitational field be directed toward the source, whatever caused it? Yes. In fact, it always is. Not only can it be, it always is directed toward the source. So gravity works, yes. What about an electric field? Can it be directed toward the source? Does it have to be? No, it can be away from the source as well, but it can be directed toward the source. So gravity, electric fields, yes, for both. What about magnetic field toward the source? Yeah, it can be. Toward the south, right? Away from the north, but toward the south. So all three of those can. What number am I looking for there? 7. 7, good. A quarter of the way there. Can be directed away from the source. Away from the source. Can a gravity field be directed away from the source? Not in this universe. Can a gravitational field be directed away from whatever causes it? What about an electric field? Away from the source? Can be. Away from a positive source. Magnetic? Can be. Away from a north pole, right? So we would say this would be electric and magnetic. Which one corresponds to electric and magnetic? 6. Good. So we got 7, 6. Now this is where it gets tricky. The reason that I put this on this practice quiz was to illustrate a point actually with this particular blank. Is inversely proportional to the distance squared. The gravitational field is gm over r squared. Is that inversely proportional to the distance squared? Yes. The electric field is kq over r squared. Is that inversely proportional to the distance squared? Yes. The magnetic field is, you don't know. You haven't been taught an equation for magnetic field, nor will you be taught an equation for magnetic force field. So how are you supposed to answer this question? The reason that I put this on there, this is actually, it's either, sometimes they release like field tested questions. So I'm not sure if this actually appeared on a diploma exam or it was field tested, but it was written by Alberta Ed. Alberta Education, who knows that you don't know the equation for magnetic field. How do they expect you to answer it? Here's the way that I tackle a question like this. I promise you that you will have been taught everything you need to know. If you have not been taught about a magnetic field equation, then it can't be the answer. Does that make sense? In the absence of having been taught that this is the relationship, you have to assume that it is not the relationship. Does that make sense? Okay, trust me and trust yourself. If you haven't been taught it, it's not the answer. So we would say this is gravity and electric field. Even if you had been taught it, it would not be the relationship. Like, it doesn't change the answer if you've been taught it or not taught it, just that if it's not an answer, we don't always teach it to you, right? So what's the answer there? We got gravitational and electric fields, so the answer for that one would be 5. 765 is directly proportional to the distance squared. Well, we know electric fields are not directly proportional to it. Either are gravitational fields. What about magnetic fields? Don't know. Therefore, you have to assume that if I have not taught you that it's proportional to the distance squared, you must assume that it is not directly proportional to the distance squared. And in fact, it isn't. If it was, if you had to include it in the answer, it would be part of the curriculum that I'm supposed to teach you, and I would have taught it to you. So that becomes an 8, right? 8 is none of them, so our answer for that is 7658. Does that